Section 20.6 Selection Rules and Intensities. In this video, I will show you an example of LMCT transition. In this transition metal complex, penta, amine, chlorido, chromium 3. This chromium has an oxidation number of 3. It's a fairly high oxidation state with +3 charges on this transition metal center. And this chromium 3+ contains only 3 d electrons. Therefore, it has empty d orbitals to accept electrons from the ligands. Now we need to look at the ligands. Supposedly, the ligands should have non-bonding electrons with higher energy than bonding electrons. Higher energy non-bonding electrons can flow into the d orbitals, the low-lying d orbitals centered on the transition metal. So that's what is going on here. The lone pair electrons from chlorine can flow into the low-lying empty d orbitals on chromium. And that causes significant change in the electric dipole moment of this transition metal complex. And this is fully symmetry allowed. We have a very large intensity here. Epsilon is roughly 10 to the power 4, a bit lower than 10 to the power 4, so nearly 10,000. Epsilon is nearly 10,000. It's really large. There are also 2 bands, DD transition bands. The epsilon of these 2 DD transition bands is roughly 10 to the power 1. So there's a huge difference. 10 to the power 4, 10 to the power 1. So these 2 have a much lower intensity, only because in an octahedral environment, all 5 d orbitals have the G symmetry. So if you look at the integral of the transition dipole moment, you are integrating a product of G, U, G. The middle U is the symmetry of the electric dipole moment. And then we're talking about D to D transition. That means it's symmetry G to symmetry G transition. And this is Laporte forbidden. But now in this case, this transition metal complex is not perfectly octahedral because we do not have 6 identical ligands. We have 5 amine ligands and 1 chlorido ligands. So this distorted the octahedral point group. So this is really a C4V point group without an inversion center. So that's why these 2 are allowed transitions, because we cannot assign the G labels to the d orbitals. There are 2 other reasons for D to D transition to occur. We mentioned one reason, the vibrations of the ligands. The vibration between the ligands and the metal may distort the OH symmetry, even if you have 6 identical ligands. Right? That's another reason. There's a third reason. So if the d orbitals are mixed with p orbitals, and then you do not have those perfect d orbitals with G symmetry, that also distorted this OH symmetry. And you can no longer assign the G labels to the d orbitals. So in that case, you can also observe D to D transition. So 3 reasons. But in the end, if you have a perfect octahedral environment, there's no PD mixing, just perfect d orbitals with perfect G symmetry. The D to D electronic transition is strictly forbidden. But again, there are exceptions. Again, over here, those are not 6 identical ligands, and there are vibrations, and there's PD mixing. That's why we can still observe DD transition, and we almost always observe those DD transitions in the UV-vis absorption spectrum of transition metal complexes with an octahedral symmetry. So again, I wrote one of the reasons here. It's not really a OH point group. It's C4V point group. Finally, I want to emphasize this again. This LMCT transition is very intense with one more condition. It has to be a electron spin allowed transition. If you flip the spin of the electron, the charge transfer transition will also have very low intensity. No exceptions.